Okay, so this is section 10.3, solving quadratic equations using the quadratic formula. So our goal of this lesson is to solve quadratic equations, which we've been solving using other methods, using the quadratic formula, and then also determining the number of solutions that a quadratic equation has using what we call the discriminant. So, yeah. Okay, so far we've solved quadratic equations already by factoring and square roots, and then also completing the square. Factoring was from chapter 7. Remember, you would rewrite the polynomial, the quadratic, as a product, and then apply the zero product property in order to find your solutions. Then we looked at square root method in section 10.1 and completing the square in section 10.2. So now we are going to be using the famous quadratic formula. And the nice thing about the quadratic formula is, like completing the square, the quadratic formula can be used to solve any quadratic equation. You might hear my kitty screaming at me for food right now. Okay. So we can derive the quadratic formula from starting with the general form of a quadratic equation, ax squared plus bx plus c equals to 0. And here's a link of a video of me deriving the quadratic formula. I think I might make another one to update it and send you. I will put as a bonus on the test a question for you to derive the quadratic formula from ax squared plus bx plus c equals to 0, and that will be a bonus. Okay, so here is the quadratic formula, and I have linked the song, but I'm not sure if this link still works, so I'll double check it and I'll update that link and send it to you guys if necessary. But our quadratic formula is x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. This won't work since this is a PDF. Okay, so using the quadratic formula to solve a quadratic equation. So remember, we find a, b, and c because a, b, and c are the coefficients to a quadratic equation in standard form. So looking at this equation, that 0 is on one side of the equation, so a is equal to 1, right? This is 1 times x squared. B is negative 3, and c is positive 1. So using the quadratic formula, I'm just going to substitute each of these values in for their variable. So we'll have negative b plus or minus the square root of negative 3 squared minus 4 times 1 times 1 all over 2 times 2a, or 2 times 1. Okay, so now I'm going to simplify what's under the radical. Negative 3, or the opposite of negative 3 is positive 3. Plus or minus, we'll have the square root of positive 5 over 2. Okay, the square root of 5 can't be simplified any further, so I can go ahead and separate my solution. So we'll have x equals to 3 plus root 5 over 2, or x equals to 3 minus root 5 over 2. Okay, so those are my two solutions, meaning if I were to substitute 3 plus root 5 over 2 in for x and simplify, the left-hand side of the equation would be equal to 0, meaning the left-hand side of the equation would equal to the right-hand side. Same thing if I substituted 3 minus root 5 over 2 in for x and simplified, we'd get the left-hand side equals to 0, and that which equals to the right-hand side. Okay, so again, using quadratic formula, I think it's helpful when you're first starting to use quadratic formula to state what a, b, and c are. So a would be -3, b is +5, and c is +2. So in my numerator, I'll have -5 plus or minus the square root of 5 squared minus 4 times -3 times 2 over 2 times -3. So again, simplifying what's under the radical. So we'll have -5 plus or minus the square root of 49. That's nice. Over -6. Now, the square root of 49 we know is 7. So when we go to separate our solutions, we'll have x equals to -5 plus 7 divided by -6, which is, that will be -1/3. Because that would be +2 over -6, which is -1/3. Okay, or x is equal to -5 minus 7 divided by -6. -5 minus 7 is -12 divided by -6 will be +2. So -1/3 and +2 are our solutions for this quadratic equation. Okay, now sometimes you're given an equation that's not ready to have the quadratic formula used to solve the equation. Just like factoring, we need to get 0 on one side of the equation in order to use the quadratic formula. So to get 0 on the right-hand side of the equation here, I would subtract 2 from each side. Okay, and now I can see what a, b, and c is. So a is 5, b is 9, c is -2, and substitute those values in to the quadratic formula. Plus or minus the square root, b squared minus 4ac over 2a. Okay, so that's -9 plus or minus. We'll have the square root of 121 over 10. So, the square root of 121 we know to be 11, so it's -9 plus or minus 11 over 10. Running out of room, so I'm going to come over here. So x is equal to -9 plus 11 divided by 10, which would be 2/10 or 1/5. Okay, and then -9 minus 11 divided by 10 would be -20 divided by 10, which is -2. So 1/5 and -2 are our solutions. Okay, for this guy we can, I would subtract 2x from each side of the equation to get 0 on the right-hand side. A is 1, b is -2, c is -4. So -b plus or minus the square root, b squared minus 4ac over 2 times 1, 2a. So 2 plus or minus the square root of 20 over 2. And we know that root 20, 20's largest perfect square factor is 4. So we can rewrite the square root of 20 as 2 root 5. And to finish simplifying here, you can recognize that, okay, I had to simplify the radical. So in the numerator, I check for a GCF. And I see that there's a GCF of 2 that I can factor out in the numerator. Okay, once I've done that, I can see that 2 will actually cancel with this 2. So I'm left with x is equal to 1 plus or minus root 5. Okay, so x equals to 1 plus root 5 or x equals to 1 minus root 5. Now you can also simplify from this step after you've separated the solutions. So like we could have said, okay, x is equal to 2 plus 2 root 5 over 2, where you could have factored out the 2 and then the 2 would have canceled. Or this can also split up to be 2 over 2 plus 2 root 5 over 2, which is 1 plus root 5. Sometimes it's easier to see that way. So then we would have 2 minus 2 root 5 over 2, which would be 2 over 2 minus 2 root 5 over 2, which simplifies to 1 minus root 5. Okay, you must simplify as much as possible, but there's not necessarily one approach. There's not only one approach to simplifying. Okay, I'm going to actually skip this one. And I'm going to skip this one too. Okay, so this is actually where we left off in our lesson on Thursday. And I don't know about you, but I don't really want to substitute negative 3/4 in for c in my quadratic formula. So since this is an equation, I am allowed to use properties of equality. So I want to drop a bomb in order to get rid of that fraction. Okay, so I'm going to actually multiply each side of the equation here by 4. Okay, the LCM of the denominators. And then when we distribute the 4, we'll have 8x squared plus 12x minus 3 equals to 0. Much better. So A equals to 8, B is 12, C is negative 3. Okay, so that's going to be the square root of 240 over 16, which that will actually simplify to be negative 12 plus or minus 4 root 15, since 16 times 15 is 240. Okay, so now it's kind of up to you. So if you want to separate your solutions and then simplify, you can. I can see that 4 is the GCF of these two terms in the numerator. So I'm actually going to factor out a 4. So I'll have 4 times negative 3 plus or minus root 15 over 16. And 4 goes into 4 once, 4 goes into 16 4 times. So we have negative 3 plus or minus root 15 over 4. X equals to negative 3 plus root 15 over 4. Or x equals to negative 3 minus root 15 over 4. Okay, so if a quadratic equation is in standard form is ax squared plus bx plus c equals to 0. The discriminant of a quadratic equation is b squared minus 4ac, which should look very familiar, right? Our quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So b squared minus 4ac is referred to as the discriminant. And we've experienced so far that quadratic equations can have no real solutions, one real solution, or two real solutions, okay? And when we start graphing quadratics, you guys will see that these real solutions actually end up corresponding to x-intercepts. But for now, we're just solving quadratic equations. It's kind of like we solved linear equations before we ever graphed lines, you know. So you can determine the number of solutions of a quadratic equation by evaluating the discriminant. So if the discriminant is greater than 0, so if the discriminant is positive, then the equation has two real solutions. So think about it. If you're using quadratic formula and the value underneath the radical is positive, you'll have negative b plus or minus whatever that value is. That's going to end up giving you the two solutions, two real solutions. If b squared minus 4ac is equal to 0, where you have 0 under the radical, well, the square root of 0 is 0. So you would have negative b plus or minus 0, where you're only going to have one real solution. It'll be negative b over 2a, right? If you add 0 or subtract 0, you're still just going to have negative b in the numerator and 2a in the denominator. And then if b squared minus 4ac is negative, less than 0, there will be no real solutions, because remember, we cannot take the square root of a negative in the real number system, right? There is no real number that when squared would give you a negative number. Therefore, we cannot take the square root of a negative number. Okay? So you're going to be able to determine the number of real solutions. It's going to feel similar, except for we're not solving the equation. We're not using quadratic formula. We're using basically a piece of the quadratic formula to tell us how many real solutions an equation would have. Okay, so A is 2, B is negative 2, C is 3. So it's b squared minus 4ac. Substituting those values in, that would end up being 4 minus 24. So negative 20. Meaning there would be no real solutions. To this equation, right? If you tried using quadratic formula, you would have the square root of negative 20, which that's not a real number. No solution, no real solutions. Okay, and then this one, A is 1, B is 4, C is 4, so B squared minus 4AC okay, so we end up with 0 for the discriminant, which actually means one real solution. And for this last one, looks like we're going to end up with a positive value. We get 65, so we get 2 real solutions. Okay, I'm going to give you a couple examples of some equations that we've encountered, where you don't necessarily have to use the quadratic equation, but have these different number of solutions. So, for example, x squared equals to -4. Looking at that, if you tried to take the square root of each side, you would end up with plus or minus the square root of -4, which is not a real number. So this is an example of no real solutions. Okay, if I give you the equation x minus 2 squared, right, and we were to use the zero product property, that's x minus 2 times x minus 2. So really we just need to solve x minus 2 equals to 0, where we get x is equal to 2. But if we were using zero product property, there's 2 factors there, right? But each factor would have the same value that would make it equal to 0. So it's really x equals to 2 twice. There's one real distinct solution, but it's almost like a double solution, because that x equals to 2 would occur twice. And then, like, if we had something like this and then use zero product property, right, we would end up with x equals to 3 or x equals to -4. So you can see that there are 2 real solutions, 2 distinct solutions, real solutions, right, 2 separate values. Okay, so my strategy for solving quadratic equations: if possible, factor the quadratic or use square root method. Those are both the fastest methods. And if you can't factor or use square root method, then you use quadratic formula, because it'll work every time if there are real solutions. You can also use completing the square method. It's valid. However, if given the choice between the two, I would rather use quadratic formula. But on your test, you will be tested on each of these methods, so you do need to know how to do each one.